Hey guys, can you hear me?
Yes.
All right, I'm working on admitting everybody here. Although Joseph Hirsch, you here?
Yes, ma'am.
Hey, you're not honors, so this is an honor session.
All right, I must have read the assignment sheet wrong.
It's fine. We're gonna do one for just everybody tomorrow. If you want to plug into that one, okay?
Okay, that's good.
All right, bye. All right, let's see here. Okay. Okay. Hey guys, how are y'all doing this morning?
Good. How are you?
I'm good. Trying to catch up on grading again. I'm gonna pull up my whiteboard for you all. Try to keep an eye out on the letting people in again. Because they changed it, I got to make sure I pay attention to it. Okay. So I'm here mostly to see how you guys are doing on the honors work, and I thought maybe we'd go over one question. I'm going to write it on the whiteboard here, and then see if you want to ask me any questions about how I do it. Now, it's going to be one that's been on homework because I only have so many of these types of questions to do. But I'm going to switch up some things about it a little bit just to try to make it so that we can go. It's slightly different. So we have the general equation. Now, can you all see my whiteboard as I write?
Yes, ma'am.
Okay. All right. And remember, this is being recorded, so anybody who's not here and wants to watch it later can. Okay. So this is the general equation, and you have data, some trials, 1, 2, and 3. Well, I don't know if I'll be able to write in between those lines super well. There we go. All right, so this is going to be the initial concentration of nitrogen monoxide. And the concentration is always in molarity. And y'all remember that molarity, capital M, is molarity, which is the concentration unit. And it's always moles over liters. Let's see. Let me let Will in. All right. Hey, Will, you there? Yeah, I see him there. Okay. All right. Back to this. I'm trying to get it to let me write. All right, I'm done. Done with this. I'm sorry, my white.
Oh.
Finally. All right, so we're going to put down the trials, and I'm just going to go through this one carefully. And ask me any questions about it. But again, the M is for molarity. Molarity is the concentration unit. It's moles per liter. And then the initial concentration of chlorine in molarity. And I'm going to mix this one up a little bit. Let's see here. Put the one there. And then you have something called the instantaneous rate over here. And that's just the rate at a certain moment. The rate changes as the concentration changes. So the instantaneous rate, and the unit for rate is always molarity per second. So you have to make sure you can plug in the units with these things because it's going to change. The rate equation will change depending on what happens with the units in the equation. So there's no set unit, and that's something you have to make sure you pay attention to. Okay, down here will be 0.76. No, 0.076. And then this one is 1 point, no, 0 point, I'm reading this wrong, 0.152. Okay, so here we have the data and 3 different trials. And you're going to try to figure out the rate equation. So the general rate equation is going to be equal to a constant, and then it's going to be times the concentration of A, whatever A is, to the X power, and the concentration of B, the Y power. And so you have to figure out the X's and Y's. The A's and B's just are the general reactants. So in this case, that can be A, and that one can be B. So I just put that in. So it's going to be a constant times the concentration of nitrogen monoxide to the X power times the concentration of chlorine to the Y power. And so we have to figure out those X and Y's, right? Now, those X and Y's do not correspond to the coefficients. So these coefficients are not X and Y. We have to calculate X and Y. That will be different actually in the next chapter that we do, and so when you'll be relieved when we get there. But for right now, we have to calculate the X and the Y. So I'm gonna put up a different color just so we're not thinking I'm using, hold on, I'm using those coefficients. So in order to calculate X and Y, we need to compare, like X has to do with this reactant. So we have to look at this reactant over here, and we have to compare two times when the concentration of this reactant changed, but the concentration of the second reactant did not change. And the reason you have to do that is if both of these guys change, like if you look at trial 1 and 2 together, this one goes from 0.5 to 1, and chlorine goes from 0.5. So both of the concentrations change. So if there's a change in the instantaneous rate, we don't know if it's due to this reactant or a combination of them. So whenever you're picking your trials, and I mixed up these trials in this particular one, like I put them in different order. Whenever you're picking your trials, you need to make sure you pick a trial where one of the 2 reactants change and the other one stays the same, the concentration level. So I can't use 1 and 2 here. So I can do 1 and 3, okay? So 1 and 3 for this one, because this one stayed the same. You see that? 0.5 and 0.5, that stayed the same. I'm just going to circle it so you see that. That concentration did not change. So any instantaneous rate between 1 and 3 is because the concentration of the first reactant, nitrogen monoxide, changed. Okay? So how much did it change? Well, it's always the bigger one divided by the lower one. So 1 divided by 1/2, this is 2. Okay? This is twice as high. And then what about from here to here? Okay, so how do I figure out that number? I take the 0.076 divided by, it looks like I got some more people I need to let in. Hold on. All right, let's see. Yep, it did all. Okay, there we go. All right, sorry guys if I didn't get you in right when you showed up. I'm not used to continuing to look down at the bottom. Anyway, what we're doing here is starting this reaction. I put up the data and we're trying to figure out how to determine the reaction rate. And so anyway, I put the general equation up and we're trying to figure out the concentration of the first reactant. We're trying to figure out the X for it. And this is just arbitrary, this X and Y, but I like to just work it this way. So we're trying to figure out really the coefficient for the first reactant. So we have the concentration difference right here, and now we're going to calculate the time that it changed here. Oh, goodness gracious. People are showing up a little bit at a time, and I have to admit people a little bit at a time. Let's see here. Looks like, no, I don't see anybody else. Okay, sorry about that. All right, so I'm going to divide 0.076 and divide it by 0.019 to get 4. So right here, this is 4. How do I get that 4? I take 0.076 divided by 0.019. That equals the number 4. That is that number, okay? So the difference is it went 4 times bigger, and the concentration is 2 times bigger. So now how do I figure out X then? I say since I increased the concentration by 2 to the sum power, X power has got to equal the increase in the reaction rate, which was 4 times faster. Do y'all follow me on that?
Mhm.
So I got the 4 right here by dividing those two numbers. It's 4 times faster if I increase the concentration by 2. So now I just solve for X, and X equals a 2. All right, so now I know that this is now a 2. So now I have to figure out Y. And to figure out Y, I've got to find a place where the concentration of the first reactant stays the same and the concentration of the second reactant changes. All right, so if you look at, I still cannot use trials 1 and 2 because they both change. But in trial 2 to 3, this stays the same. So I'm going to circle it. And then 2 to 3, this changes. You see that? 2 to 3, that changes. Okay, now I'm going to divide the larger one by the small one to get a 2 again. And so I'm going to divide, so since I did the top one divided by the second one, I have to divide the top one by the second one. You see what I'm saying here? I take 1 divided by 0.5 to get 2. So that means I have to take 0.152 divided by 0.076. So in this case, I take 0.152 divided by 0.076, and I think that's also a 2. It is. 0.152 divided by 0.076 is 1.97, which is a 2. So if I divide, I guess what I'm trying to say here is notice that if I divide this one by this one, so 1.00 divided by 0.5 is a 2, then I have to divide that top one by that one in the same way. I have to do it in the same order. Okay? So increasing this concentration by 2 increased the reaction rate by 2. So 2 to the Y power equals 2. So Y this time equals a 1. Hold on, I gotta turn my phone off. There we go. So 2 to the Y power equals a 1. So now Y is a 1. Do y'all follow what I did there? Does anybody have a question about that one? Nobody's got a question? All right. So that now I can keep working on this rate equation. So the rate equation is going to equal K times the concentration of nitrogen monoxide squared times the concentration of chlorine to the first power. And so, you know, you don't have to write a 1 there, but if you do, you don't get it wrong. Okay, now we have to figure out K. So after the first job we do is figure out X and Y. The second job we do is figure out K. All right, so first we figure out X and Y, and now we're going to figure out K. And how do we do the K? Well, we pick any trial. It doesn't matter which one. And we put all the data into the spots. So let's see, on my answer key, it looks like I used trial 3. So in order for you to see that it works no matter which trial you use, I'm going to use a different trial. I'm going to go ahead and, well, I used trial 3, which was the 1 and 1. I'm going to use trial 3 here, which is 1 and 5. And that's because what I did was when I copied this down, I mixed up the trials so that you could see that it's not use trial 1 and 2 and then trial 2 and 3, but that so you could see, you compare the trials to see one of them changes and the other one stays the same. All right, so this time I'm going to go ahead and use trial 3. I'll put an asterisk beside it. And I'm going to fill in the concentrations into the formula. The R is this value here. So 0.076, and you have to put the unit meters, molarity over seconds. S is for seconds. So how much is the molarity changing per second? It's going to equal K. And then what's the concentration of NO? NO is 1.00 molar. You have to put the unit in the formula, molar squared, times the concentration of chlorine is 0.5 molar. Do y'all follow me there? Okay, all I did was I took all the data from this trial and put it into the formula. Now you'll notice we have everything rather, but we don't have K, so we're going to solve for K. And when you're doing this, whatever your exponent is, you got to make sure that you use that for not only the number, but also for the unit. So I'm going to divide both sides by these two quantities. So I'm going to divide by 1.00, because 1 squared is 1, right? And then m squared is m squared. So we have to square the molarity right there. And so I'm dividing it by this, 1.00 molarity squared, and I'm going to divide it by 0.50 molar. So that on the right side of the equation, this cancels out, and we just have K by itself. All right, now we're going to do the math. The math is the easy part. So I'm just going to say 0.076 divided by 1 divided by 0.5, and I get 0.152. Okay, and then I have to figure out what the unit is. So the number is not ever the hard thing to do on this side. It's to get your units correct. And it's because we're going to deal with a complex fraction. So we have molarity over seconds at the top divided by molarity squared times molarity, which is molarity cubed. You follow me on that one? So now we just have to simplify this expression for the unit. Okay? Okay, so when you divide by the, when you have a complex fraction, you basically multiply the top and the bottom by the reciprocal of the denominator. So this is over a 1. So 1 over m cubed, I'm going to multiply the top and the bottom by 1 over m cubed. Y'all got that? Give me some thumbs up. I see Will, somebody else. Give me some thumbs up. Emma, Luke, you there? Anna? Okay, cool. All right, now what I'm going to do is cancel out those units. So obviously the bottom goes away, numerators and denominators. Now we got to look up here. We have one of the m's. It cancels one of these m's, so that now is a 2. Okay? So the final unit is 1, because 1 times 1 over s and m squared. That's the unit, 1 over sm squared. You got that? So what is then K? K is equal to 0.152 1 over sm squared. This unit is not the same for K every time. It changes depending on every equation. So you cannot just plug that in. You have to figure out the unit each time. The unit is always dependent upon the x and y values. Okay? Now I can finally get the final rate equation. So the rate equation then is going to be equal to whatever K is that we just calculated. So 0.152 1 over sm squared times the concentration of nitrogen monoxide squared times the concentration of chlorine to the first power. So that's the rate equation. Now I need to ask you some questions. Okay, about this equation. What is the order of this reaction with respect to nitrogen monoxide? What would it be? Somebody tell me. See if I can pull up some more people here. All right, Savannah Stewart, can you tell me what the order of this reaction is with respect to nitrogen monoxide?
I don't know.
All right, the order of reaction is one, it's really an easy concept. The order of reaction is just whatever the value is of that exponent. So the order of the reaction with respect to nitrogen monoxide is 2. Okay, so Savannah, what's the order of the reaction with respect to chlorine?
1.
1, that's it, that's all it is. Okay, so that's a 1. Now what does that mean? It means that when I change the concentration of nitrogen monoxide, the rate changes a lot faster, because like if I think about it this way, if the concentration of nitrogen monoxide went up by 2, then 2 squared, it would go, the rate would go 4 times faster. If I change the concentration of chlorine by 2, 2 to the first power, it'd only go twice faster. Okay? So the order of the reaction with respect to some component is just whatever the exponent is. Now, if I ask you what is the overall order of the reaction, you would just add the exponents together. 2 plus 1 is 3. Okay? All right, Jonathan, do you have that? Okay, good. All right, now I'm going to erase, well, no, I can't erase without erasing the whole board. I haven't figured out how to just erase a piece of it and come back yet. Like, I've tried it, and then I lose my pencil. So if this is the rate of reaction, and I triple the concentration of nitrogen monoxide, how much faster is the reaction going to go? So it doesn't matter what the concentration of nitrogen monoxide is. I'm going to give it an X. There's an X concentration of nitrogen monoxide and an X concentration of chlorine. If I triple the concentration of nitrogen monoxide, that would be 3 times as much, right? But the concentration is squared. So how much faster would this reaction go then? It would be 3 squared. So 3 times 3, it would be 9 times faster. Or is that right? Yeah, 3 times 3, 9 times faster. If I triple the concentration of chlorine, since it's only a 1, so whatever the concentration of chlorine was before, now there's 3 times as much. There's only a 1, it would only go 3 times faster. You see that? Okay. All right, so now what we're going to do is we're going to figure out, so the rate, we're going to figure out the rate of this equation if nitrogen monoxide's concentration is 0.4 molar and chlorine's concentration is 1.6 molar. We're going to figure out what the rate is. So all I do then, if these are the how much we have, we just plug them into the formula and calculate it. That's all it is. So the rate then would be 0.152, 1 over seconds molarity squared times 0.4 molar, because that's what I just said for that, and that has to be squared, times 1.6 molar, and that has to go in that spot, 1.6 molar, I gotta put the M there, to the first power. And now I just do the math and figure out what the rate is. Now, what's the unit for rate up here? Sorry, the unit for rate is molarity per second. So when I get this done, it should stay, the unit for the rate should be molarity per second. Okay, so I'm going to multiply 0.4 squared and m squared. And I don't know what that number is, so I'm going to put it in my calculator. 0.4 squared is 0.16. Oh yeah, 0.4 times 4, 16. But then it's m squared. And then 1.6 molar. And then 0.152, 1 over seconds times molarity squared. Okay, now we're going to multiply all the numbers. So 0.152 times 0.16 times 1.6. So I get a number of 0.0389 By the way, I'm not going to worry about your sig figs on these questions like this. Okay, guys? I'll give you grace on that. So now let's figure out units. Okay, so we have meters, molar squared times molar. That's molar cubed on the top. And that would be this times this, divided by seconds times molar squared. And then I just have to simplify this unit. When I simplify the unit, there are two m's that take away two of these, that becomes a 1. So it ends up being just molarity over seconds, and that's what the rate unit is, molarity over seconds. So you see, it's important that these exponents are the right values. Okay, so I'm willing to take a question about this one or about any of the other parts of the chapter. So let me hear you. Anybody have a question? Have you guys attempted these questions yet? Good, I see Caitlin. Let's see, Annie, have you tried these questions?
Yes.
Okay, how are you doing okay with them?
Yeah, I'm doing fine. I'm having my sister help me when I need it.
Okay, okay. Jan, how are you?
I'm pretty good. I'm really tired, so I'm surviving.
You're really tired. Did anybody have to go to the basement last night?
3 times.
We finally went down there and just stayed.
Yeah.
So, Anna, how are you doing?
I'm doing good.
Are you understanding the rate equation stuff here?
I am. They're actually pretty kind of fun.
Good. I'm glad to hear that. I know that they do rate equations in chemistry in college. I'm not sure if they do them in first semester or second, but I do know that this rate equation, I mean, the ones you're learning now are just the beginning of it, so it'd be good for you to master these. Jonathan, how about you? Okay. Caitlin, you okay?
Yeah, I'm fine. I get it. It's not too complicated.
See. Tiffany, how are you doing? You feeling well?
Yes, ma'am. Thank you for asking. The only thing that I have to like think about, or like really, I don't know, the units kind of
Mess you up?
the units are harder for me, but like trying to figure out if it's like m squared or how like you end up with the unit, but like
Okay.
my sister's also helping me too. So.
Okay. Yeah, the units are the trickiest part, and that you have to go through all this portion right here to be real careful with it. It's that complex fraction thing. I would make sure that you look at the example problems really well and see where they all came from. I was trying to hunt down some more example problems in my chapter, and I don't have too many more without pulling up the ones that are on the test. Obviously, I can't do that. So, yeah.
Sounds like a great idea.
Yeah. Emma, how are you?
I'm good. I get it now, so that's good.
Okay. I guess another part of the trickiness of this, besides the unit, is making sure when you do your comparisons up here, and don't assume you always do trial 1 to 2 and then 2 to 3. Always look for only one of them can change. Only one reactant can change, and the other one has to stay the same. So like here, from a 0.5 to a 1, that changed, and then 5 to 5 stayed the same. So the change over here from 0.019 to 0.076 is because of that rate, because of that concentration change. The chlorine did not change, so any change over here is due to this one reactant. So you just got to always make sure only one of the reactants changed concentrations. And it does not matter which 2 trials you compare. You just have, I mean, it matters because you got to have only one of them change. But what I'm saying is, it's not 1 to 2 and then 2 to 3. It's 2 trials where one reactant changes. Just be careful about that. All right, Savannah, how are you doing?
I'm doing good. I mostly got the math. I just didn't know like the order.
Okay, yeah. The ordered reaction is just those exponents. Will, you doing okay?
Yeah, I think I got it. It's just getting back into the groove after not doing it for a week.
Yeah, yeah. Because the test is Wednesday, and we do have, because of an administration has said you have to take the test on the test date. So make sure you're doing your homework before you're taking the test, okay? Because I know the homework could be not counted late until after Sunday, but then it wouldn't help you very much if you don't do the homework before you take the test. Anna, you doing okay? Anna Garner.
Yes, sorry. My dad called me.
Oh, no problem. All right. I'm trying to look and see if I've talked to everybody here. It looks like I've got everybody down. Does anybody?
Sorry, she was talking to me.
Yeah. Anybody have another question before this is all I was really planning to go on, because everything else is pretty much the same as general chemistry. You know, the catalysts, the inhibitors, figuring out today's homework is reaction mechanism. So you'll be watching that. It's not super hard, but I'm gonna have a Zoom session tomorrow if anybody needs to review that stuff. Again, it's also optional. Okay. Are we good?
Yep, I'm good.
Okay. All right. Well, I'm going to go ahead and stop the meeting then. I'm going to save this and put it up for other people who weren't here. And then if you wanted to review it, you can do that. Okay. All right. You guys have a great day. Talk to you later.
You too.
Bye.
Thank you.
Bye.
Anna.
Hmm?
Say hello to your father for me.
Oh. Okay.